Let's start lecture 13. The course is corrosion protection methods, and today we will start a topic on materials aspect of corrosion protection. Topic will be corrosion protection. Now, if we look at the materials, mainly metals and alloys, just by adding some element we can improve the corrosion resistance few orders of magnitude. Like let us say in a steel, let us say carbon steel, we add chromium, and let us say the chromium is added more than around 12%, the material will have extremely high corrosion resistance. And that is the philosophy that is considered for designing stainless steel. One of the popular stainless steels is 304 stainless steel, which is wash basin kind of application. In fact, it has more specific applications in biomaterials, where it is not 304, rather 304L, where L is called low carbon. So, now if you see that the carbon content is reduced from around 0.08 to 0.03 or 0.02, that time we call it low carbon stainless steel. And again we have chromium about 18% and nickel is about 8%, and those are all in weight percent. So, then what we are trying to do is we are trying to create a passive layer on the metal surface, so that it does not allow for the dissolution of the underlying metal just below the passive layer. And another thing what we are doing by reducing the carbon content is to avoid chromium carbide precipitation along the grain boundary. So, now you could notice that by doing a composition design, we are actually having a better corrosion resistance. Similarly, let us say we have a kind of carbon steel, and on the carbon steel if we have a glassy coating, okay. So, of course, this will come in the coating section, but still if we have a coating, amorphous coating, by having some processes like APS, which is atmospheric spray coating, or atmospheric plasma coating, the full name is atmospheric plasma spray coating, or HBOF, high velocity oxyfuel coating. In that method, by using those methods, one can deposit amorphous coating on top of a normal plain carbon steel. So, once we actually create amorphous coating, so we introduce a great extent of corrosion resistance. Now, here you see the base metal does not change its composition, but just doing the surface modification, we are actually having great deal of corrosion protection. So, this is again on the structure part, which is of course introduced externally, but still that is actually coming due to composition effect, because not every material will convert to glass. We have to choose the proper composition to make it glass after deposition. Okay. While cooling, it will convert into glass, but that composition we have to select, specific composition we have to select. Now, this is again on the aspect of composition and modifying the surface. Now, let us say we have another instance like processing. Okay. So, the material processing is not independent of materials. For example, if we have a casting, let us say we are going for a welding, because a long material we cannot make a seamless product, sometimes we have to use welding. And during welding, if we have a rapid cooling after welding, we can introduce a lot of stress into it. Okay. So, those are actually residual stress. and that residual stress, if we have, it can actually reduce its corrosion behavior, corrosion resistance. And in fact, the corrosion behavior, corrosion resistance could be so poor that it can also lead to a fracture or the crack in the material. Okay. Now, this is on the residual stress part where it gives a negative impression on the corrosion protection. Now, we have to have processes to relieve that stress. We call it stress relieving operations. We have to do it. But again, while doing that, we are actually making change in the material. Okay. And that leads to change in the corrosion behavior of the material. Now, this is on the aspects of processing effect on the material. Now, there could be possibilities of surface modification, right. So, instead of doing any coating, if we make the surface smooth or reduce the roughness, we can introduce a lot of corrosion protection. Like, let us say if we want to introduce a good amount of fretting corrosion protection. Okay. Fretting is a effect where you will experience for a meeting surface under stress, and if we have a very small amplitude vibration, and that time we can experience fretting. And so, if we have a smooth surface, the fretting can be reduced. In fact, cavitation can also be reduced if we have a very smooth surface. Fine. So, that means again, by just doing the surface modification without putting any coating or anything, we can also introduce a lot of good corrosion protection to the material. So, that means we have to understand this materials aspect of corrosion protection. Fine. We have talked about design aspect where we are not touching the material part. Only if sometimes we are not touching the material part, rather we are only looking at the geometry part or metal connections part. Those are the things we have considered in case of design modification for corrosion protection. But when we talk about materials aspect, we have to talk about composition, we have to talk about microstructure, we have to talk about processing related change in the material, which can lead to a change in its electrochemical behavior and also subsequently corrosion resistance. And finally, we would see that it would also lead to affect is performance, and here performance is about corrosion performance. That means how resistant that material will be towards some corrosive where that material is supposed to be used in practical application. Right? So, let us talk about those parts. Now, whenever we talk about materials, we have to talk about composition. Fine. What material it is? It can be single element, it can be multi element. Now, most of the cases, if we consider only metals and alloys, there is a very limited application field for the pure metal. But if we consider the application field for alloy, it is huge, enormous number application field. But still, so that means whether it is element or alloy, we have to take care of the composition, okay, and its effect on the corrosion behavior. So, the composition is a factor. So, when we talk about composition, that composition along with processing, it can lead to change in structure. Now, that structure change could be crystal structure change or that could be change in the microstructure. Fine. For example, let us say iron, steel, if we had around 0.002% carbon, okay, so that time we will mostly observe a single component, single phase structure like ferrite, okay, or if we have a structure carbon steel with 8% nickel and maybe 1% manganese, we will see that it is single phase austenite, right. So, that means here the crystal structure is FCC, and in case of let us say very low carbon, let us say Armco iron, there we have a very low carbon, it is almost pure iron, where the structure would be BCC. Right. So, that means here by changing the alloying elements, we can make a change in the crystal structure. So, like in case of very low carbon, not other elements, we have BCC structure. In case of low carbon, at the same time little manganese and a very high level of nickel, it can get into FCC structure, which is single phase austenite. In fact, stainless steel is basically 304 is a austenitic stainless steel, that means the phase is only austenite, whereas a pure iron is FCC, BCC, which is ferrite or single phase BCC structure. Fine. So, that means composition would have an effect on microstructure or structure. Simply if we put structure, so this structure could be crystal structure, it could be microstructure. Okay. So, there could be two situations. Now, that could be mixed also. It can have change in crystal structure as well as microstructure, because the morphological distribution of different phases, or even a single phase. If it is a single phase, let us say austenite, it can be fine, it can be coarse, or it can be mixed. That means there could be a presence of fine grains as well as coarse grains. So, those variations are possible. So, these are about composition and structure. Of course, there would be effect on the processing. For example, if we maintain a same processing, let us say furnace annealing we are doing, let us say we are having 0.1% carbon steel, 0.2% carbon steel, 0.8% carbon steel. Okay. So, there if we do furnace annealing for both cases, all those three cases, we will see that gradually the pearlite content will increase, and 0.1% carbon steel, there will be a very least amount of pearlite and mostly ferrite, but as we increase the carbon, the pearlite content would increase, and at 0.8% carbon we will see 100% pearlite. So, that means we are processing, that means different composition, same processing, we have different microstructures, as well as crystal structures are also changing. For example, in the beginning everything is to be converted into austenite when we do the heat treatment, and from austenite we are getting, so that means from FCC we are getting ferrite, which is BCC, as well as we are getting cementite, which is of a different complex structure. Right. So, that means same processing, we have different microstructure or a different composition. But let us say we take 0.3% carbon steel, we do furnace annealing, we get ferrite and pearlite. Now, if we do quenching, we will get martensite. If we do austempering, we will get benite. If we do a cyclic holding at around 780 degrees Celsius, so that means close to the eutectoid temperature, we can get spheroidized structure, where those ferrite will be a grain structure, but those pearlite colonies, the cementite lamellar, which will convert into a small spheres. So, we call it a spheroidal steel. Fine. So, that time you see the change in the microstructure as we change the processing. So, that means it will have a direct effect because of difference in processing. So, that means if we say processing, okay, we can have direct effect on the composition structure. Fine. So, we have direct effect. Now, here if we try to list those processing, what could be the different processing? Of course, here we are talking about heat treatment. Okay. So, heat treatment is a processing. Now, if we start processing, first thing what you have to consider is the casting. Okay. Because every material first we have to melt, and then we have to prepare the material, that means we have to reduce the ore and then get to the metals condition, and most common process is basically the casting route, and in fact in the casting route we can also prepare the final product also. Fine. So, this is a processing route which is casting, and the casting, it actually involves melting plus solidification. Fine. In fact, if we consider casting part, let us say steel, in one case let us say we take around 3.1% or 2.9% carbon steel, and there if we do casting, let us say we take it to temperature around 1100 degrees Celsius, where everything will be molten, because I am considering the cast iron part. So, if we do a casting without converting the material into graphite, we will get a structure. but if we cool slowly and if we add silicon, then what we will get? We will get a structure which consists of graphite and ferrite or pearlite, depending on the cooling rate we are employing. Now, if we do rapid quenching or rapid cooling from the molten state, we will get a structure called white iron, where the structure would be, it will be austenite plus cementite. It becomes very brittle and generally ledeburite forms. So, there the structure becomes very strong, but it is very brittle. Okay. So, you could see that just by changing the processing, we are getting different structures, and all those structures would have different corrosion effect or corrosion behavior or electrochemical behavior. So, the casting part is considered here. So, that means we have casting, then we have working, and working means I am talking about mechanical working, and in this particular case we are considering rolling, forging, wire drawing, all those processing factor. In fact, there will be a strong influence of those processing on the corrosion behavior. Then we can take up another mechanical working which is not related to the rolling, forging and wire drawing. Here we are actually doing material removal. In those working case, we do not do material removal, rather we keep the volume constant and we generally change the shape. But in case of mechanical working by removal of material, we call it machining. In case of machining, we finish the material, okay, and that time we can actually change the surface condition. We can make it rough, we can make it smooth, all those things would have again effect on the corrosion behavior or electrochemical behavior of the material. Now, in the machining, one can have like grinding or milling. So, those are some of the machining practice, okay, or turning. Then we have another one which is called heat treatment. Right. So, for example, machining, we can also talk about the surface stress, right. The machining can influence the surface stress condition. It can be beneficial or it can be bad, okay, towards the corrosion resistance part of it. So, it can lead to a extra bit of corrosion resistance, or it can also have a kind of poor influence on the corrosion resistance. That means, corrosion resistance can fall. So, those possibilities are there. We will give some examples on that, but it actually can influence the structure, which is here, it is the surface structure as well as subsurface structure. When you do machining, if we consider the machining part. So, when you do machining, let us say we are doing a machining part, let us say this surface is machined. Let us say we have a structure like a pearlitic structure. So, let us say that this is the pearlite, okay, which are lamellar structure of cementite and ferrite. If you do machining like this, machining movement is like this, the cutting tool, there could be possibility of alignment of those features along the surface. So, this particular thing can become like this, okay, and it would definitely have influence on the electrochemical behavior of the surface, right. So, that means it can also change the microstructure. In fact, machining can also change the composition of the surface. If the heat content at the surface is very high, there could be possibility of decarburization even, fine. So, that means if we talk about steel, a little medium carbon steel, if we do machining without having a proper cooling agent, the surface can get decarburized, so that the surface electrochemical behavior would change. So, those possibilities do exist. So, that means processing would affect the composition or structure and then subsequently corrosion behavior, fine. Now, when we talk about all those factors, they can introduce something called stress. So, the stress can be internal So, it will be kind of a subset. So, this can introduce stress, all those factors can introduce stress, and this stress residual in nature, fine, and that residual stress can be bad or can be good. For example, if we have, let us say, welding, okay, we missed one more thing, which is welding. So, let us consider that welding part. So, that means joining, and here joining means welding, brazing, soldering. Here we are not considering riveting or bolting, because that time we are introducing different materials, and that time we have to look at the design aspect of it. Okay. But if we talk about welding, brazing, soldering, that can introduce different materials in that structure part, and that different materials can introduce galvanic effect. But apart from galvanic effect, that can also lead to stress, residual stress, and that residual stress can be bad. For example, in stainless steel, where we have knife line attack, in case of a stabilized stainless steel, let us say 316 stabilized stainless steel, where we have titanium or niobium presence, that means we do not allow chromium carbide to form by having some elements in the material in a small quantity, which will have a higher affinity towards carbon. So, that means even if carbide tries to form, the carbides will be titanium carbide or niobium carbide, which will form uniformly throughout the material, but chromium will remain constant along the grain boundary as well as in the grain body, and there will be no chromium depleted zone, and it will not have intergranular attack. But if we do welding of the stabilized stainless sheet metal, there could be possibility of knife line attack. So, we have discussed that knife line attack in the earlier lectures. Okay. So, please look into that. So, that is what I am talking, that stress factor. The stress factor can be in situ. There are two possibilities, in situ, fine. That means during joining part, during cooling, we are actually having those stresses, residual stresses, that is in situ. But there could be ex situ stress, like short pinning, fine. So, there we can actually having this short pinning part in the mechanical working. Actually, here we can introduce short pinning, fine. So, short pinning actually introduce compressive stress, and that compressive stress can actually prevent corrosion fatigue related failure. So, that means it actually improves the corrosion protection. So, ex situ one example is short pinning and it leads to compressive stress, prevents corrosion fatigue, fine. And in situ, definitely if it is tensile related, fine, that might lead to stress corrosion cracking, that can lead to intergranular corrosion, it can lead to pitting, all those possibilities exist. So, that means we have to also look at the stress part, and since the stresses are coming due to processing, we put it here actually in this particular group, the working related or processing related stress evolution in the material. In fact, stress can actually change the material structure. This is interesting. For example, if you take some material, let us say a material with a very high level of glass forming ability. So, the glass forming ability, we consider it as the material which has a higher degree of formation of amorphous material, fine. So, that means it, so if we have those atoms are, let us say those atoms are distributed in a regular fashion. So, let us say in 2 dimension, let us say these are the atoms in a material, those are sitting in a regular fashion, we call it crystalline. Now, if we do working over there, let us say we do ball milling of a material with this crystalline structure, and at a particular critical stress level, because when we do ball milling, we keep bombarding those powder materials and keep giving impacts by 2 impacting balls, and there could be several degrees of impact, like ball impacting against the wall of the ball mill, that means the valve, or between 2 balls when they are colliding, there could be also impact on the powder, and the powder will be sandwiched between the 2 powders or powder, the ball and the wall, the media wall. Now, when we do that, the stress level can be, and every time when we do that impact, little bit of strain is associated with it, and when we have strain, that means we are introducing dislocations. So, or defects, you can say. As we introduce defects at a particular critical strain level because of the stress impact, so the material atomic arrangement can be irregular or it can be random. So, when we have a random atomic arrangement, but the material is actually solid because it has a very high degree of viscosity. So, shear movement of atom is prohibited there or very sluggish. So, we call it a very solid, but with the structure part we consider it to be amorphous. So, the atomic arrangement would be very irregular, and but it will be solid. So, that time we call it amorphous. So, now once we have this crystalline to amorphous structure, and this happens because of the application of stress. And that time the material electrochemical behavior would vary, and in fact, most of the cases when we convert amorphous from crystalline, the material corrosion resistance improves. Why? Because the amorphous material has got no grains, we will not have any grain boundaries, and we know that the grain boundaries are the susceptible area for corrosion to start, and since it has no grain boundary, it would have high degree of corrosion resistance. And now we talked about the effect of stress, and we could see that the stress is actually coming due to processing, and that is what we are incorporating in the processing segment, and that has a relation to the structure, and that would have a relation towards electrochemical behavior or corrosion behavior. Now, once we incorporate this, then actually what we are seeing, this processing is leading to some change in the electrochemical behavior. In fact, when we talk about electrochemical behavior, it is basically talking about property, right? We are talking about property, and in fact, when we talk about property electrochemical behavior, if we see change in structure as well as composition, crystal structure or microstructure, we are also having some relation like this. It has influence on the property electrochemical behavior, and this is nothing but corrosion behavior. Right? Now, if we consider all those 3 parts, composition, structure, processing and as well as property, when we have those effects, it is actually having influence on the performance, materials performance. And here if we talk only about the corrosion performance, okay, it is getting influenced, because in a favorable condition like favorable stress condition, favorable structure condition, we can have a good degree of performance in terms of excellent corrosion resistance. in that particular use. And whenever we use any material, it is very difficult to think of some use where we do not have any corrosives, okay, except for example in vacuum it's difficult to have any corrosion or corrosion would be very low, okay, but that particular situation won't arise in normal engineering application field, right. So that means if we see, it has its effect on corrosion performance, or we can say corrosion protection, and if we talk about performance, it talks about durability, okay. So that means it is actually related to performance of the material, fine. Now if we look at this again, if we consider processing, it has effect on composition structure, it has effect on property. So that means it must have effect on performance. So it is also related to performance. Now considering property, electrochemical property is actually guiding the performance. So it is also related to performance. Now if we look at this particular picture, this does not talk anything but the material tetrahedron. So we are talking about materials tetrahedron. So when we talk about corrosion behavior, we talk about materials tetrahedron. Now in the material tetrahedron, one thing is not incorporated here. So that we have to just introduce if we talk about corrosion resistance of the material. Now we will see later that many of the cases in engineering application field, the corrosion resistance is decided by the performance of the surface film, and the surface film or the passive layer or the oxide layer that forms on the surface, oxide or hydroxide that forms on the surface, and that passive layer could be in situ or could be ex situ. Here we are talking about in situ passive layer, that means when the material reacts with the environment and forms some surface film. There could be possibility of adding some polymer coating. So we are not talking about that. So that comes under polymer on the coating aspects. But here we are talking about passive film, and that passive film would also have a deciding factor. We will talk about those passive films in our next lecture, but that should be introduced in this particular material tetrahedron part. Now when we talk about passive film, it is actually coming in the composition and structure region, because we are changing the surface composition when it forms after reacting with the surface film, after reacting with the corrosive, and also its structure also changing because of that typical structure of the typical structure of the passive film. So let us introduce that particular part in the composition and structure region. So we call it passive film or surface film, fine. So that would also have influence on the property and finally on the performance. So let us actually stop here. We will continue our discussion in our next lecture, and some of the aspects what we have considered here in the material tetrahedron towards corrosion protection will be dealt with by giving specific example. Thank you.